Okay, so welcome all on Understanding Kotlin Coroutines. I have a very ambitious plan for today because I want you to understand Kotlin Coroutines. And by understanding that, I would like you to know why do we need Kotlin Coroutines. The most ambitious part, how do they work? Because it's not obvious at all, and most Kotlin Coroutines developers don't know it and don't need to know it, but it's amazing how it works under the hood. And then we'll learn about basics of Kotlin Coroutines library. So for those who don't know me yet, my name is Marcin Moskała. I am an inventor of kt.academy, an official JetBrains partner for education. Mainly, I started as an Android development. Today I work as a trainer, teacher, and consultant. And you might know this blog where there are quite some articles about Kotlin and different things. So why do we need Kotlin Coroutines? And let's start from the simple question, how much front-end developers do we have in here? Front-end, people who do Android, websites, something like that. Okay, and how much back-end developers do we have? Spring, Cater, a few of them. So I believe those are two different words, and there are different reasons for each of them. They're totally dealing with different problems. So we'll talk about them separately. So starting from front-end, since I see that front-end dominates in here. The typical Kotlin problem in the front-end is that we need to get some data from a repository. It's either API, maybe it's some database, whatever repository. And this is a time-consuming operation. Then we do some processing with that, and finally we displayed it on the view. Pretty simple. Simple presenters, view models, controllers. Of course, it never works like that. First of all, we cannot get from API on the same thread where we do everything else. It's like there is one thread in Android to all operations. So if we waste it on waiting from API, we won't be able to do anything on Android. So we need to start it on a separate thread. But if we start in a separate thread, you cannot modify view because it can be only done from the main thread. So you need to get back to main thread, which is an acceptable solution, but I think you can all agree it's terrible. You are allocating many threads, you are just moving from thread to thread. It's not really a good solution. What alternatives do we have? A very simple one, callbacks, of course. So callbacks is like, okay, start it now, start your API request, and tell me once you are done. Once you are done, call this code from this internal function. And this is fine. Some technologies use callbacks very intensively, for instance in Node.js. But callbacks are fine for a very simple cases. When you have a bit more complex cases, you have some problems. So first of all, it's very hard to make them simultaneous. So if you wait for this callback, you cannot in the same time send another callback and wait for that. It's hard to design it this way. So in this case, it's not simultaneous. You could send those two simultaneously. It's hard to do with callbacks. Second of all, with every callback, you need to deepen and deepen indentation, what causes many problems. In general, it's hard that if you want to do something after this code, you cannot just place it after this code. You need to place it inside its callback. So it makes it pretty hard to design in more complicated cases. And this indentation and these results, these problems that we face, even have their own name. They are known as callback hell, exactly. You can really find extreme callback hells, especially in Node.js applications where callbacks are used very intensively. And this is bad. In Android, how much Android developers do we have in here? Okay, in Android, how much of you use RxJava? Yeah, so this is our solution, the RxJava. And this is the first problem. You can see it's slightly more complicated than what we've seen on the first slide, you know. We need to set up observable, say where we subscribe, where we observe. We need to set up a subscription. This is a good solution. I have a bit more wrapping, overwrapping, but on the end, it's quite a good solution. The other problem, you can solve it simultaneously, but it's even harder. You need to remember that you have function zip. You need to wrap data into a pair. You need to destructurize it into data, and everything gets quite nasty. And I think you all have experience when your RxJava grow too much in your projects, and it was quite hard to understand what is going on and not simple to debug either. So yeah, it's a good solution, but it's quite a complicated solution. So now, coroutines for help. So the first problem in Kotlin Coroutines looks like that. Solution looks like that. You can see that this part looks exactly as what we had at the beginning. It's a simultaneous solution. But we wrap it in this coroutine. And what this coroutine allows is that this function can be a suspending function, meaning that it can stop execution, like we send API request, we stop execution, we release thread, we don't need to hold UI thread for this time, we release this thread, and when we have our result, we grab it again and we start where we finished. So to make it possible, we need a new capability to stop in some point, release thread, and start where we finished. We'll get back to that. Other problem can be solved in the following way. This is not the best solution because this is an alternative to the callbacks, where we wait for the first one. Once it's done, we wait for the second one. It's done, we wait for the next one. It's flat. It looks good, but it's not simultaneous. But it's already a progress. We can make it simultaneous using async functions. What is a news? In most languages, async await are built-in keywords. In Kotlin, we don't need async await. Async await are functions. This is a top-level function, extension top-level function. It returns an interface disposable, and await is a method in this interface. So just Kotlin Coroutines can give us capability to make async await without anything extra. Let's take a look at backend, because there are also some backend developers in here. And in backend, we are dealing with slightly different kind of problem. So the typical problem in backend looks like that. We get some data from database from another part of a system, maybe from subsystem. Then we do some processing, and then we respond it. This is a very simple response to our call. Of course, it never looks like that. All our requests cannot run in the same thread, because soon we will waste our thread. It will be blocked. So what can be done is that we can wrap it into and start everything either on new thread or maybe on some pool of threads, what is done by default by most frameworks. There is some pool of threads, and we take one that is not used at the moment, and we use it, which is, I would say, okay solution. But what needs to be understood is that this operation, database or waiting for some other subsystem, might be really expensive, time-consuming. And this operation might be needed very, very often. For instance, let's say that we need to take 200 milliseconds to get data from database. Then we have 10,000 calls per second. It's imaginable, yeah? If you do the big system that is used by many users, 10,000 requests, it's not nothing huge. Okay, so you need to serve it. If you would have absolutely optimized system, you would need to save it about, am I calculating right, 2,000 threads? 2,000 threads. One thread takes 2 megabytes on the RAM. 2,000 threads is 4 gigabytes of RAM only to maintain threads. This is unacceptable. And this is a big problem that JetBrains wanted to solve. And it was solved during Kotlin Coroutines because, as we said, in Kotlin Coroutines, we never await on thread. We don't waste this precious resource. When we don't use it, we release it and we let other threads to use it. So this can be a suspending function, and once we need it, we acquire thread again. And to visualize it, I wanted to show a very simple simulation. So imagine that here we have a coroutine, and we have thousands of calls in the same time, and we await for 1 second. And we do that in the coroutine. So in thread, it's not possible. It's too much thread to use. In coroutine, it's not a problem because we use threads only when we need them. So when you start this solution in coroutine, you can see for a second nothing, and then you have all the dots. You can start it again. Nothing, 1 second, all the dots immediately. Trying absolutely the same code with threads, boom, error, and few dots. This is exactly how much threads it was able to maintain before we got out-of-memory error. It's just impossible to allocate this amount of threads in the same time. And by making them slip, we waste this precious resource. So, this is why. The big question is how, and I will highlight how does it, I will highlight to make you understand what is happening here. So this is a sequence builder known from Scala. Sequence builder calculates new value on demand. It's lazy. So for instance, in this case, we enumerate over this sequence. So when we ask for the first value, then we start in the top, we print ln1, then we return first value. Then we can print it. Then we ask for the next value. We print 2, and then we return it, and we can print it. Then we ask for the next value. There is no next value, so we only print e, and we finish. You can see that we stop exactly after yield, and we get back when we need next value. To visualize it even more, in this example, we have the same sequence, but in here we produce iterator, and we only take first value. And what is important, I could take this iterator, I would hold it for a month, then I could serialize it and deserialize it, and then I could start it again, and it would print 2 and return 2. We can stop in the middle of a block and get exactly to this point whenever we want. So at this point you probably think, wait a moment, I am programming for years. I know how functions work. One does not simply stop function in the middle to continue it later. Well, one does with Kotlin Coroutines, and to show you how is it possible, I will show you what is going on under the hood. Are you ready? Okay, so we will start from this very simple function. It has one suspension point, delay, okay? There is something going on before, there is something going on after. One suspension point. What is this delay? This delay is, I will share this presentation on Twitter, so if you don't need to, if you can find me on Twitter, Marcin Moskała, you will find all the slides there today or tomorrow morning. So what is this delay function? It's totally different concept than thread sleep. It's a function that suspends coroutine and releases that after a moment. To see how it works, this is the old implementation. Right now it's a bit more complicated, but the initial JVM specific implementation looked exactly like that. So delay suspended coroutine. This is a Kotlin primitive, suspend coroutine. But before it suspends it, it schedules executor to resume continuation. Resume continuation. This continuation, we'll talk about it in a moment, this continuation contains the rest of our coroutine yet to be executed. Continuation, every continuation implements an interface. This is exactly how this implements looks like. This is the new look, this is the old look, but you can still use resume and resume with exception thanks to extension functions. This is easier to discuss about it. So continuation contains rest of the state to be resumed when we want to go on. Okay? And there are two ways how we can resume it. We can resume it with resume, meaning that if we call resume on continuation, it's like delay returned unit. We can also resume it with exception. Resume with exception is like delay throw an exception. But of course we can call this resume much later. So we suspend and we schedule to continue, and by this continue it will work exactly the same as if we were returning unit from delay, but with a result. Okay? It will slowly start making more and more sense. So we have this continuation. And it's time for our most important slide. We'll see what this simple get config is compiled to. Don't be scary, we'll talk about it line by line. So first thing you can see is that this get config has an additional argument, which is an outer continuation. We don't use it in here, but it can be used to suspend outer coroutine. Okay? We don't need it in here, but we will see. But in delay, it's used to suspend delay and to resume get config. So we get some continuation, and then we wrap it into our special class. So for each suspending function, there is a special anonymous class generated which contains whole state. This class implements continuation interface. So this continuation is special for every suspending function, and it contains rest of the state yet to be executed. One thing that it contains is the label. In this case, label is always there. Label says in what point have we stopped. In the beginning, label is equals to 0. That's why we start at the top. But if label would be 1, then we would jump directly in here. Okay? So imagine that we start this get config, and there is we start the get config, and there is no suspending in the middle. Just imagine for a second. So if there is no suspending, our label is 0 at the beginning, so we enter this if, we print A, we set label to 1, delay, if it wouldn't suspend, then it would return unit. So if it wouldn't suspend, then this wouldn't be true. We would enter label equals to 1, print B, and return some config. So without suspension, works like a normal function. With suspension, we start with label equals to 0, we print A, set label to 1, delay, suspends coroutine, meaning that it returns coroutine suspended. And this coroutine suspended propagates up. To visualize it in here, we have started get config with some continuation. We wrap it into our special class. We pass it to delay. Delay schedules continuation, and it suspends coroutine. And this is all that is going on. for a second. After a second, continuation resume is called. Continuation resume, this is a class generated for this particular function, so it can call this suspending function. So it calls resume with, which calls our getConfig, and we jump exactly where we finished. And we can return some config and finish our function. So getting back to our function, when resume on continuation was called, getConfig was called with reference to the continuation. Label was set to 1, so we jumped in here, and we continue like normal. You will have it all in YouTube and in Twitter, these slides, so you can take a look a bit more and analyze it line by line. But it basically explains everything, except of one question. But what if our function holds some state? What if there are some inner variables? And you can guess that they are holding the continuation, but to show you how does it really work, I decided to show one more function, a bit more complex because with 2 suspending points and with some data that are necessary after resume. So when you compile it to JVM bytecode, you will see something that looks a bit like this. Very similar to the previous one, but one big change that you can see is that in the beginning, we try to read data from our continuation. If those data are there, then, if those data are there, then we can use them. And at the beginning, they are not there because they were not set. But imagine that we started our function, label is 0, we set label to 1, we get config, and let's say that our getConfig suspended coroutine. It suspended coroutine, finished. We propagate coroutine suspended up, and we release our thread. But after some time, our data came from API, and the resume with our config is called. So our continuation knows, it can see what is the label, so it knows for what data do we wait for. So it will set this data to the continuation config, then it will call presenter on create, and we will have this config already filled, and we will jump into another state. If getConfig wouldn't suspend, then it would fill our data, and we will directly jump into label 1. Does it make sense? Anything to clarify? Might be a bit confusing, but this is like a holy grail of programming. People were working on coroutines since 60s, maybe 70s, but I believe the concepts were already in 60s. And the first well-implemented coroutines, as far as I am concerned, arrived in Go like a few years ago, and they are a bit limited, and Kotlin Coroutines is, I think, first really powerful coroutines implementation. And yeah, the code is not so big. So, looks like magic, but under the hood, what is there to be known is that everything is held in these continuations. All the state of our coroutine is in these continuations. It has some properties. And it means that if we would want to serialize this continuation, we would have to serialize these properties as well. But we can do that. And if then we would deserialize it and we would call resume on this continuation, we would resume our function exactly where it was stopped. Magic. So, as you can see, it's simple. What is there to be understood is that there are two concepts. There is Kotlin Coroutines support and Kotlin Coroutines library. And they need to be distinguished. What we are talking about right now is Kotlin Coroutines built-in support. It's something that is built into Kotlin, and you have it when you use Kotlin. But Kotlin Coroutines library is something that you need to add library for. The difference is pretty big because Coroutines support is pretty minimalistic. It has only suspend modifier and few primitives that are necessary there. Kotlin Coroutines library is pretty big and has many functions. Kotlin Coroutines support can be used to reproduce absolutely any style. And if you don't believe, you can check it out. Really, JetBrains did a lot of experiments, and style of concurrency in Go, Haskell, JavaScript and C# are very easy to reproduce. Absolutely any known popular concurrence style can be reproduced with Kotlin Coroutines support. But it's not easy to use just without any special library. And to make it really useful, we have Kotlin Coroutines library that gives you one concrete concurrence style. And to make this knowledge in here useful for you, let's talk about this Kotlin Coroutines library. So we'll have Kotlin Coroutines library 101. So as we said, to start suspending function, you need to pass continuation. And you don't have it there, meaning you need to start suspending function from another suspending function, but it needs to start somewhere. And we started in so-called coroutine builders. So this is our starters for all coroutine contexts. So the simplest one is launch. Launch is like you are launching Rocket and you forget about it. People very often say it's similar to a thread. You launch a thread and you can forget about it. So when you launch two things separately, they will both go concurrently. But your main function will not await for those launches. They are like daemon threads. I mean, they are not really like daemon threads. They are just not holding thread when they are await, so you will finish without finishing them. So without this thread slip, you wouldn't have anything printed. For this problem, we have another coroutine builder that is called run blocking. So run blocking looks like an opposite of coroutine because it's delaying. When we suspend, we are holding the thread. What makes sense in two reasons. In the main function when we don't want to finish before we finish everything, and in the unit test functions where we have the same case. And those are two cases where we use run blocking. Of course, in this case, it doesn't make sense. We would just make everything simultaneous. We'll first delay, then print A, then delay, then print B. It does not make sense. But how it is used is like that. We say that we wrap everything in this run blocking, and then run blocking will await for all its children, will say soon, why is that? And the last popular coroutine builder is async, which is like a launch, but for a value. Async has its await, which returns a value, and async is there for value. There are many consequences of that. For instance, errors are thrown in await, not in async. So we have three coroutine builders. There is also one more thing that you might have noticed when we were showing our initial examples. What is this? This is some magic argument passed to our coroutine builders, and this is called coroutine context. You've seen it in continuation. So coroutine context is a universal holder of data. You can pass there anything. It's like a collection, but a special one because each element is collection at the same time. It is done so that you can add element plus element. It's also a coroutine context. And there are four most important coroutine contexts. I mean, if you do your own coroutines library, you can make whatever coroutine context you want. In Kotlin Coroutines library, there are four key coroutine contexts. One, coroutine name. You can name coroutine for debugging purposes. Job is a life cycle of coroutine. You can use it to cancel coroutines or you can use it to await for coroutines. We have coroutine exception handler, pretty useful, and universal exception handler for many coroutines. And finally, we have coroutine continuation interceptor, which is like a God class. It intercepts continuation, so it can be used to do everything. And the most popular use of this coroutine interceptor is coroutine dispatcher. So coroutine dispatchers change the thread on which we run our coroutine. The default one, dispatcher's default, is using a thread of pulls. By default, number of those pulls on this number of these threads on this pool is equal to number of cores in your processor, because those threads never wait. They are always used, so it does not make sense to have more threads in this pool than you have cores in your processor. Then you have main. Main is only present on platforms that have some main threads. For instance, in Android, in iOS, because you have Kotlin native that also supports coroutines. On JavaScript, it's of course the main thread. In Tornado FX, you also have main thread. So it's not always there, but it's your main dispatcher if you are doing Android development. It will be your UI thread. Then you have IO thread. It's a single thread. We use it to not have logs that are printed in the same time by few threads, you know, this mess that you have when two threads in the same time print something on console. So this is why we switch to IO thread. And finally, uncoffined, I don't care what threads do I use, take the first one that you use. So it does not dispatch at all. So coroutines dispatcher, you as an Android developer will mainly use those two. This one to do changes in views. This one to do network request, database request, basically everything else. Unless those are suspending functions, then you can do everything on main. But if you don't want to do calculations on main thread, it's good to switch to default as well. One more thing is that you don't really start launch without any context. We either need to start it, we need to start it in some scope. What is scope? Scope is basically a holder of coroutine context. But what is important is that each coroutine in this block, this is Lambda expression with receiver, it has coroutine scope. So it makes a relationship between coroutines inside coroutines. This is a part of a concept called structured concurrency. So for instance, when you have run blocking, wrapping launch, then you can get rid of this global scope, and right now launch will be a children of run blocking. Being a children, I mean being a parent, it means some responsibility. And one of responsibility of parent is to await for his children. You don't wait, you don't leave shop without your kids. So you don't need this delay on the end anymore, because run blocking will not finish until launch is finished. And that's why it's so easy to wrap everything with run blocking, and you can do 10 launches, async awaits, and you will never finish until this all is finished. Structured concurrency is a very powerful subject, but it's a subject for a separate presentation. There is a very good presentation from Kotlin Conf about it, I recommend you. But for now, it's a really nice concept of having these children and parents and their responsibility. You can shape your concurrency in your program in a really nice way. Since you are mainly Android developers in here, I wanted to show you a very simple usage, but making very much sense, usage of coroutines in your project. So let's say that you have MVP. You can also have MVVM, but for the sake of simplicity, I used MVP. And what you can do is that you can make your presenter implement coroutine scope interface. When it implements coroutine scope interface, it needs to give this coroutine context property. And in this coroutine context property, we'll have few things. We'll have dispatcher's main, so we'll do everything on a main thread by default. It's a very simple use. You can, if you have some calculations, it's good to switch for default. But the simplest use is to have everything on a main thread. You will never wait for anything anyway, because you should do every long operations suspending anyway. Then you can have the default handler for all your coroutines. So this is what will happen if you have an exception in coroutine. You will just call view on error with this error. And I believe in most applications this is what we do. We just pass this responsibility, and it's probably handled by some main activity, by some base activity, or base fragment, or whatever, or maybe by each activity separately. And then we have this supervisor job, which is like a job, but it has one special property, is that not stop when one of its children is gone. It's like, okay, we don't care if one of our children is gone, all others can live fine. So this is why I use supervisor job instead of one job. And since it has a single job and all those will run on this job by default, on the end you can do cancel when you destroy this view. So if you escape your application, you cancel your coroutines, and you don't wait for responses on your. This is if you use RxJava, most of you use RxJava. This is where you call dispose, where you dispose all your disposables in RxJava 2 or your observables. No, cancel can only work in suspension point. It cannot work during computation. But we assume that we are most likely awaiting for something, or we are done. So yeah, so this is a very simple use. Of course, most of that you can hide under the carpet into some base presenter, and in your main presenter you can only do these launches. And on the end, like nearly for free, you can have really nice. You can have really nice and pretty effortless concurrent system where you have default exception handler, everything on the main thread but suspending, and you cancel when you destroy. So nearly everything what we use RxJava for in, I would say, vast majority of cases. Am I right? Now, of course, you can go deeper into coroutines and do much more, but this is a very, very simple example that is enough for most projects. Coroutines are very well supported by most libraries. The concept is popularized very quickly. In Retrofit, who is using Retrofit in here? Yep, majority. In Retrofit, there are a few adapters. One of them wrote by Jake Wharton. All you need to do is that coroutine adapter, and what is returned then is a deferred. Deferred is the same as what is returned from async. So it has this await function method, which is a suspending method. So effortlessly good coroutine system. Then we have some frameworks. For instance, Ktor, pretty popular Kotlin framework, has built-in concurrence. When you say what endpoints do you have, those are all coroutines by default. So in this case, get accepted news data, it's a suspending function, and it's not a problem. We are in a suspending context by default in Ktor. We also have testing libraries. For instance, mock. It's a very popular mocking library for Kotlin. It supports, it allows us to mock suspending functions and to verify suspending functions. It has a very good support for coroutines. So all tools are there. You can go and use it. And that's everything I had for you. Thank you for your attention.